Right. So as Mike mentioned, I'm going to talk about some work we've been doing with JWST and the CEERS survey in particular, looking at or trying to identify AGN out to the epoch of reionization and what these systems tell us about early black hole growth. So most of the results I'll be talking about today are based on data from the CEERS survey. CEERS is an early release science project that was selected back in 2017 to test and validate a variety of different observing modes on JWST. We were awarded 63 hours to cover about 100 square arc minutes in the EGS field. And you can see our footprint here. The gray here is the previous generation WFC3 observations from HST, and then our overlapping observations are shown in the different colors there. The main selling point for CEERS is that we tried to get overlapping observations of several different instruments and observing modes, and that's one of the reasons why there's this kind of jumbled mess of things in that footprint. So we've got observing with the NIRCam imager, which is a high resolution imager on JWST that's sensitive out to about 4 microns. We've got several pointings of the minifred imager MIRI that's sensitive out to 21 microns. And then the real workhorse with that for CEERS has been the NIRSpec spectrograph, which has this fantastic micro shutter array that allows you to perform multi-object spectroscopy. And so we've been taking spectra of hundreds of sources, and that spectra has really given us the most surprising results. And so all of our observations were completed as of December 2022, and they're now publicly available for anyone to use. And there's been a variety of different science results that have come out of CEERS. But like I said, arguably the most surprising is the detection of faint broadline AGN out to relatively high redshifts. So the first of these sources is shown here. This is CEERS 2782 at redshift 5.24. And it was targeted because it was in this relatively red, and you can see its morphology up here. It's point-like, and much to our surprise, it had it superimposed on its H-alpha narrow emission line. We think we see a broadened component there. So this broad component has a full width half max of about 2,000 kilometers per second, which can translate into a black hole mass of about 10 to the 7 solar masses. Now, in this source and in most of the broad sources that have this broad component, we actually detect the oxygen 3 line at a higher signal of noise than we do the Balmer lines. Yet we fail to detect any sign of a broad component in those forbidden lines. And so this, we interpreted this to mean that we weren't in fact seeing an outflow component here, but we were instead seeing emission from the broadline region of an AGN. And so this was our first source. Our second source that actually made it into that first paper from last year is shown here. This is CEERS 746, also point-like in red. And here we can see an unambiguous broad component superimposed on that H-alpha, that narrow H-alpha line. For these fits, we can fit the narrow component to the width of the O3 lines, and we always need that broadened component to get a proper fit to these Balmer lines. And so these sources, we can basically take the continuum luminosity of these sources or the H-alpha luminosity and convert it into a bolometric luminosity. And what we find is that these systems are about 2 to 3 dex fainter than existing samples of quasars at redshift 4 to 7 that were known in the pre-JWST era. And so here the red and orange points are the CEERS known broadline AGN, basically, these things are sitting about a factor of 10 to 100 below in bolometric luminosity compared to known quasars. And in terms of their black hole mass, they're about 2 orders of magnitude less massive than those pre-existing, or those quasars known in the pre-JWST era. In many ways, these systems are closer to local AGN than they are the high redshift AGN known at redshift 4 to 7 previously. So this kind of gives you a sense of the power of JWST to find these faint sources. Now, the thing that I find most amazing about these systems is that they are really quite numerous. Several studies have now found dozens of these faint broadline AGN with NIRSpec data. So these are plots from Ichi Hirakane's sample in CEERS, Europe Matthie's sample, and then Roberto Maiolino's sample from the JADES data set. And there's a lot of these things. And so right away, just given the numbers that we're detecting, you can immediately infer that the number density of these things would be much higher than you would expect based on much higher than bright quasars, because we're talking about relatively small fields here. We're talking about fields that were, you know, the EGS field and the Good South field, and so in fact, you can calculate the UV luminosity function for these sources. That's what's shown here. This is the UV luminosity function for from Europe Matthie's study, and then from Roberto Marilino's study. The orange line here is the number density expected for QSOs identified from the ground at redshift around 5. And the number density of these type 1 AGN that are being found by JWST is shown in this red line here. So we're talking about, you know, factors of 10 to 100 times greater than would have been expected based on just the number density of bright quasars identified from the ground. And so they're really quite numerous. In addition to being a lot of them, a lot of these things kicking around, we can also calculate the mass of, or roughly estimate the mass of the host galaxy and compare that mass to the black hole mass. What's shown on the left here is an estimate of the black hole mass versus the stellar mass of the broadline AGN detected in CEERS. And in this plot, I've done a really simple thing where I've said, let's assume all of the light from these sources is coming from a broadline, from the galaxy. And we know that's not the case because the SEDs of many of these sources look like type 1 AGN. So it looks like we're just looking at QSO light. But let's say, for the sake of argument, that these things are simply all powered by galaxy light. This gives us an upper limit on the mass of the host here. And we find that even with this extreme assumption, that these systems are scattering above the local black hole galaxy scaling relationship, which is shown in gray here. And so we've known for quite some time that high redshift quasars identified from the ground scatter above that local relationship. That's essentially these blue points here. So that's always been attributed to selection effect, that maybe we're picking up the tip of the iceberg at these high redshifts. And so these things naturally might scatter above the local relationship. And what we're finding now is that even as we go to lower volumetric luminosities, lower black hole masses, we still are finding that these higher redshift broadline AGN are scattering above the local galaxy black hole scaling relationship. This plot on the right is a plot from Fabio Cocucci's recent paper where they did a more detailed study of this. They actually took into account selection effects, and they show that even given the observational limits of what type of broadline AGN you could detect, it looks like the sources that we're finding scatter above the local relationship at greater than a 3 sigma level. Now, one of the reasons why these overmassive black holes are interesting is because it places constraints on black hole seed formation, or at least the formation scenarios. And in fact, it tends to favor the direct collapse seed formation scenario. So just as a reminder, there's lots of different formation scenarios that have been proposed. Some of them produce light seeds, some of them produce heavy seeds, but the direct collapse scenario predicts that you should have a relatively massive seed, with a mass of 10 to the 4, 10 to the 5 solar masses that directly collapses into a black hole from primordial gas. And since that is thought to occur before a galaxy forms a substantial amount of its stars, one of the predictions of this direct collapse scenario is that galaxies will start off with overmassive seeds, and then the galaxy eventually catches up so that the system sits on the local relationship. And so since we're finding these things scattering above the local relationship, it tends to favor this heavy seed or overmassive scenario. Now, that is based on this ensemble population or broadline AGN that we're detecting. We also have single individual sources that place interesting constraints on the potential seed masses. So this is a broadline AGN that was identified in CEERS by Rebecca Larson at a redshift of 8.67. And here now H alpha is shifted outside of the NIRSpec detection window, but we can see H beta, and we see again signs that there's a broad component to that H beta line, much broader than the neighboring O3 lines in the spectrum. And so in this case, if you calculate the black hole mass, again, gives you something about 10 to the 7 solar masses at a redshift of 9. And so this single source, the extreme redshift of this source starts to place interesting constraints on the formation scenario of this object. So for example, if this thing formed via direct collapse into a massive seed, then this thing could have formed at around a redshift of 15 and then just grew at its Eddington rate. And that would naturally explain its appearance at around a redshift of 9. However, if you think the light seed scenario is the way that this thing formed, well, you'd have to push the formation epoch back to around a redshift of 20. And even then, you would need episodes of super Eddington growth. And that's essentially what this step function is showing here. So essentially, either way, we're placing interesting constraints on how this thing formed. If we think the Eddington limit really is the limit here, this thing had to have been formed as a massive seed, or basically we're going to have to exceed that limit. Now, it turns out this is not the highest redshift AGN identified with JWST. There have been two other record holders. One is an X-ray detected AGN at a redshift 10.1 that was published in this paper by Bogdan. And then the current record holder is GNZ11 at a redshift of 10.6 that Roberto Mailino put out using the JADES data set. And it turns out both of these sources also tend to favor the overmassive seed scenario. Now, what I'd like to talk about for the rest of the talk is an interesting subset of these broadline AGN that have become known as little red dots. About 20% of the broadline AGN that we detect have this unusual spectral energy distribution such that they are extremely red in the rest frame optical and relatively blue in the rest frame UV. It turns out that, no dust extinction law works this way. That typically, if something is really red in the rest optical, it's also going to be pretty red in the rest UV. And so it looks like these sources have a UV excess. They look like they're bluer than they should be in the UV. So this right away tells us that there may be multiple components, multiple emission mechanisms going on in these sources. So one way to explain this SED shape is that you have a reddened galaxy shown in green here, a massive reddened galaxy with blue light from the central quasar coming through, or central AGNs coming through and giving this UV access. Or on the flip side, it could be a relatively blue galaxy with a heavily reddened AGN that's giving this power law rise in the continuum at long wavelengths. The interesting thing here is if you look at the morphology of these sources, they are point-like at all wavelengths. So for example, in this scenario, you'd expect that the galaxy would dominate the emission at these long wavelengths. But in fact, the source looks point-like at those long wavelengths. And in fact, the stellar density required for this to be a galaxy at long wavelengths is really quite crazy. This would be a 10 to the 11 solar mass object that's unresolved. Right, some of the estimates of the size of these things is on the order of 100 parsecs, and so you'd have to have 10 to the 11 solar masses of stars crammed in an extremely small space. And so one of the alternative explanations that we presented in our paper from last year is that perhaps we're just looking at QSO light at all wavelengths, that we're looking at a relatively obscured source. So this has an AV of 4, and then we're looking at some scattered light at short wavelengths due to patchy obscuration. This is something that's seen in hot dogs at lower redshifts, where you have things that are extremely red, but then still have this blue UV excess due to scattering at short wavelengths. Now, it turns out that one of the things we wanted to do is we wanted to identify sources with this unique spectral SED and do so photometrically. And so in a paper led by Guillermo Barro, we looked at doing this using a two-color selection. So this is 277 minus 444. Things that are red in the rest optical tend to, at around a redshift of 5, tend to percolate to the top of this diagram. And then here we're looking at 150 minus 200. And so things that are blue in the rest UV move over to the left. And so using that those two colors, you can pretty effectively pick out these things that have this blue plus red spectral energy distribution. And if you look at the morphology of those sources that were selected based on their color, they're all point-like. And so these are the sources that have been dubbed little red dots in the literature. They essentially have, they're red in the rest optical, they're blue in the rest UV, and they have point-like morphologies. And interesting enough, Jenny Green followed up a sample of little red dots in the uncover field with spectroscopy and confirmed that about 2/3 of these sources actually show broad lines. And in fact, if you throw out the sources that we think are brown dwarfs tend to be a little bluer in the rest UV than the rest of the sample. Then in fact, about 80% of the things selected as red dots show broadline components in their NIRSpec spectroscopy. And so one of the things we did in a recent paper that we put out is we tried to identify little red dots, not using a color combination, but instead using continuum slope measurements in the rest frame UV and the optical in order to extend the search for these little red dots to lower redshifts to see if we can find lower redshift analogs for these things. And so essentially what we did was we measured the slope, the continuum slope of objects using shifting band passes that essentially always ensure you're sampling the SCD redward and blueward of the 4,000 angstrom break. And so here we're down at redshifts 2, we're basically relying on HST data and some JWST data. And then out at redshifts, we can go all the way out to redshifts at 8. We can measure the continuum slope using the reddest bands in NIRCam and the relatively blue bands in the UV. And we did this for a variety of different fields: the CEERS fields, the primer data set, the JADES fields in Good South. And so we did this with as much photometric data as we could get our hands on. So here's some examples of our spectral fits. This is a little red dot at a redshift of 4, 6, and 8. And again, you can see that we're basically measuring the continuum slope using 3 different band passes that are always above or below the Balmer break. And so doing this, we actually selected a sample of about 341 candidate faint red AGN that have this unique spectral slope. And we took a lot of care to remove things that remove contaminants. So for example, I mentioned that brown dwarfs tend to be relatively blue. And so this is a case where we remove things that have a UV slope that's too blue. This is an example of a brown dwarf. We've also done careful work to remove extreme emission line galaxies where we think that the red continuum slope is actually coming about as a result of emission line contamination in the broadband photometry. So in this case, this is the 277 filter, 356 and 444, and here the 410 medium band filter reveals that in fact the continuum slope is probably flat, and this upturn is just due to H alpha and then O3 contaminating the broadband photometry in that case. And so at the end of the day, we've got a sample of about 341 little red dots in these different fields. This is just a color image of these things. They are all point-like. They look relatively unresolved. And remember, I mentioned that the goal here was to try to identify lower redshift analogs of these things so we could try to figure out what exactly is going on with their SCDs. And in fact, when we look at the redshift distribution of these sources, we find that they are relatively rare at redshift less than about redshift 4. These things really do start to increase in their number density around redshift 8. There's a lot of them between 5 and 7, and then they basically peter out at around a redshift of 4. And we don't see similar things with these particular colors at redshifts 2 and 3, and even at 4. And so this led us to wonder in our paper whether this was just a natural consequence of inside-out growth, that maybe it's in fact the host that's obscuring these sources, because essentially at redshifts 5, 6, and 7, you've got this concentrated star formation activity going on at really small scales. You're building up the bulges of systems, and that may actually obscure the growing black hole. And then as you get to lower redshifts, as star formation moves out to larger scales, then that dust is no longer deposited directly within the vicinity of the central AGN. And so you end up getting these relatively more unobscured sources appearing. Based on this the photometrically selected sample, we can also now calculate the number density of these things. And we find a similar problem that I discussed earlier. This is the UV luminosity function at a redshift of 5 here and a redshift of 7 on the right. And the QSO, the number density of QSO is based on ground-based surveys is something down here. So essentially about 2 orders of magnitude below the number density of these little red dots, which are shown in red here. And just to illustrate the problem here, this line here is the UV luminosity function of known X-ray AGN at redshift 5. And so these obscured sources, which we think are just a subset of the overall AGN population at these high redshifts, their number density is already higher than that of X-ray AGN at redshifts of 5. And so presumably this is going to get even more problematic as we move out to higher redshifts, because the number density of the little red dots doesn't decrease significantly when we get out to redshift 7. Yet we know that the known AGN population is in fact going down. Now, within our sample of photometrically selected little red dots, we have detected the first 2 X-ray detected sources. So this is a source at redshift 4.66, spectroscopically confirmed to be at around a redshift 4.66, and it's X-ray detected in Cosmos. And in this case, our SED fit indicates that this source is the rest opticals dominated by disk emission, reddened disk emission, and then you can see a hot dust torus contributing at long wavelengths that's constrained by that 24 micron point there. And our SED fit here indicates that the rest UV should be dominated by the optical light of the host. And in fact, when we subtract off the central point source, we do in fact start seeing signs of the host in this case. And so in general agreement with our SED fits. Now, this source has enough counts that we can actually do a spectral analysis, X-ray spectral analysis. And what we find is that this thing has an NH of about 10 to the 23.3 per centimeter squared. So not quite Compton thick, but moderately obscured, as you might expect, given how red this thing appears. A second source that we identified that was X-ray detected is in the good south field. So this has a photometric redshift of 3.1. And again, in this case, we find that this thing is well fit by a reddened AGN emission in the rest optical, and then blue light from the host coming through. And you can see just based on the morphology, that central point source pretty much disappears at 115, at 1.1 microns, which would be right around there. And again, here we could do a spectral analysis, and we find this thing has an NH of about 10 to the 22.7. So again, moderately obscured. It turns out these are the only 2 X-ray detected sources in our sample of about 400 sources. And we think that's the case because these things are the 2 brightest little red dots in our sample. In fact, we can calculate the bolometric luminosity of these sources, and they have bolometric luminosities of about 10 to the 47 ergs per second. And so that, which would imply an alpha OX of about 1.8. And so we think that the reason why we're detecting these particular sources is just that they're the most luminous little red dots in our sample. Now, if there's any doubt that these things are in fact really AGN, we actually do have NIRSpec spectroscopy of 24 of the sources in our sample. This is spectroscopy taken by the JWST survey. We were fortunate that JWST completed its observations just as we finished up this paper, and so we took a look to see whether the sources we claimed were faint red AGN in fact showed broad lines. And what we found was that between 70 and 80% of these sources, in fact, showed broad lines with widths about 1,400 to about 4,200 kilometers per second. So it's a general agreement with the previous study that previous numbers that Jenny Green found with using the uncovered data. And so many of these things are unambiguously AGN. We see broad lines in multiple Balmer lines, and then it ranges between 70 and 80% depending on what signal and noise you cut on for that broad component. Interestingly enough, about 25% of our little red dots show narrow blue shifted absorption in their emission lines. And so 3 of these sources, for example, show narrow absorption lines in their H alpha emission, which immediately tells us that there is dense low ionization gas present within the dust sublimation radius of these sources. And I say that because as I'll mention in the next slide, we don't detect strong mid-infrared emission from these sources. And so this must be dust-free gas that's relatively close and is partially covering the central engine in this case. And it turns out these similar absorption lines have been detected before. This is 2 sources that showed such features in Europe Matthie's original paper where they defined the little red dot selection. And so we know that, for example, broad absorption line quasars tend to be X-ray weak, and it's largely explained by absorption. Of course, these lines are not as broad as ball quasars, but we do see signs of absorption in the intervening lines of sight. So I'm going to end with just 2 open questions. One is, where's the obscuring medium? It turns out that if you look at the mid-infrared emission of these sources, we don't see signs of a hot dust torus in many of them. This is a figure from Christina Williams' paper where they stacked the mid-infrared emission of several of these little red dots. And what they find is that after this red continuum, red optical continuum, the STD relatively flattens out. And we would expect if there was a hot dust torus there that basically this thing should start to rise at long wavelengths, and we're not seeing that. And so this right away tells us that perhaps these systems lack a hot dust torus. And in fact, it could be that LRDs are primarily host obscured as opposed to obscured by gas that's within that's close to the central engine. So it could very well be that just that there's a large column density of intervening gas and dust in a really small space in the host, so larger scales. And so that essentially would move that reprocessed dust emission to longer wavelengths where MIRI wouldn't be able to detect it. And the second open question is, why are so many of these things X-ray weak? So these are two figures from Roberto Maiolino's recent paper where they did an X-ray, Chandra X-ray stack in the China Deep Field South, where they find essentially for all of these type 1 AGN at redshift greater than 4, they're not seeing any stacked X-ray emission. And in fact, if you just do compare their bolometric luminosity to their X-ray luminosity, these sources would live up here. So essentially, they're really X-ray weak compared to the general AGN population. And so the question is, are these things intrinsically weak, or are they heavily obscured? It could very well be that there's a broadline region that's dust-free and has a covering factor of 100%, so just covering the entire thing. So it's not Compton thick, so emission from the broadline region can get out, but you're not seeing that reprocessed dust. Or it could be something like these things just lack a hot corona, or they have a weak hot corona, and so we're not producing X-rays. This is, I think, something that's a really open question that needs to be addressed in the future. So let me end there and just put up my summary slide and take any questions you guys might have.
Great. Yeah, that was a really great talk. So if anybody has questions, Chris, I see your hand up.
Yeah, no, thanks for a great talk. One basic question. I mean, you're finding a very large number of these objects in what is not a huge footprint.
Yeah.
So does this have any interesting implications for the Sultan argument? I mean, you must be adding a lot of energy to the global, black hole radiation field. And so do you sort of burst the budget in terms of the Z=0 black hole mass?
Yeah, it's a really good question. Most of these sources where we actually, for the spectroscopically confirmed ones at redshift 5 and 6 and even 7, we find are not actually growing by crazy amounts. They're growing at like 10% Eddington. And they tend to be above that local relationship. So presumably these things will stop growing and the galaxy is going to catch up. Whether that causes problems, I don't know. They don't look like they're growing like gangbusters at moderate redshifts. I don't think that might not be the case for the things at redshift 9 or so, but the things at redshift 5 and 6, they look like they're just kind of growing at 10% anything. So perhaps we're finding a lot of them, but so that means that their duty cycle is high. So they have to fold both of those things in, but I don't know whether it causes an issue.
Okay, thanks.
Great. Yash, did you have a question?
Yeah, hi. I had a quick question about the X-ray detected sources. So you mentioned at the end that they're a possible idea is that some of these sources may not be obscured by gas dust near the AGN itself, but by the host. Yeah. So would you have to change how you model those sources if they are X-ray detected? Because I'm not sure exactly which model, like if this assumes obscuration by something close to the AGN or not.
Yeah, so these fits were done with Segal, and the Segal does in fact, these fits are done with assuming a clumpy torus, nearby. But it turns out the two X-ray detected sources do in fact have, they have a 24 micron detection in this case. They actually are detected in the mid-infrared, and so it actually allows for that dust torus. That dust emission is essentially what causes the second upturn here. So the X-ray detected ones, in fact, look like we might expect them to. It's the other sources that are the ones that are not X-ray detected that seem to lack this hot dust torus. In fact, it's very unusual because the sources that have, for example, these Balmer absorption lines, you might expect there's gas nearby. Maybe it's re-radiating in the infrared, and these things essentially have non-detections. It's not even that they're weak in the mid-infrared. We don't actually detect them in our deepest MIRI observations.
So
Thank you.
Yeah,
cool.
so we would have to change that model. We'd have to fit it with like the Nemkova models, which do this often, will have a single temperature, and so they peak at the same location all the time. One way that you would need to change this is to basically have cooler dust, so essentially warm dust as opposed to hot dust, that would move this thing to move that peak to longer wavelengths.
Okay, maybe one or two more questions. So Massimo, or do you have a question? Or Mia? Sorry.
Hi, actually, it's Mia who has a question because I'm watching with Massimo. I was wondering, given that you're talking sort of 10, if I understood right, 10 to 100 times the number of AGN that we expected, what implications does this have for the reionization budget?
Yeah, that's a really good question. It turns out we don't think these sources contribute significantly to reionization just because they're super faint in the UV, in the rest UV. And if I can find it, I'll swing back to the example plus. You can see these things have a magnitude of like 29th magnitude in the rest UV. And so we don't actually think they're putting out a significant amount of UV light just because they're super faint.
Great. So I'll ask the last question. I'll take the speaker's prerogative. So, the X-rays are weak, but there's a lot of other ways to measure the bolometric luminosity, using the optical continuum, using high ionization lines, using the mid-infrared. Are they offset in that the X-rays are really weak, or are they just bolometrically weak by other, all wavelengths or something, which might suggest a different emission?
So one interesting thing you could do is calculate the bolometric. You could calculate the bolometric luminosity using the 5100 angstrom continuum luminosity, or the H alpha broadline luminosity. And there's that correlation between the H alpha broadline luminosity and the continuum luminosity. And Jenny Green showed in her paper that in fact, when you compare those two, you find good agreement with what you would expect for type 1 QSOs, just once you dered in the 5100 angstrom luminosity. And so it does look like in many of these, the rest optical is dominated by AGN light based on that continuum luminosity. And so you can take that continuum luminosity, calculate a bolometric luminosity, and then that's where you start getting into problems because they tend to be relatively bright. They tend to have bolometric luminosities 10 to the 46, but we don't see them in the X-rays. And I think that's what Roberto was showing in this plot here, where basically the bolometric luminosities are relatively high, divided by essentially a lack of detection. So here's their bolometric luminosities. So somewhere between 10 to the 45 and 10 to the 46 for these sources.